coming up. The first one is by Bondell. Howard's at NC State, used to be at Rutgers, and he's done a lot of really nice work in variable selection, various forms of dimension reduction coupled with regression, both from a frequentist and Bayesian perspective, as well as a wide variety of applications. So,
thank you, and I'd like to thank the organizers for inviting me here. It's a nice workshop to be at. Again, being down the road, it's convenient to come, except when you misjudge the traffic in the morning and get here 5 minutes before your talk is supposed to start, but got here on time, so it worked out well. So I'm going to talk a little bit about, so this is a Bayesian approach, but it's kind of also a hybrid Bayesian frequentist approach, which is one of the things I like to do is work on the interface of the two methods. Okay, so just to give you a quick idea first, as outlined, I'm going to talk a little bit about just the general problem of high-dimensional variable selection. I'm going to focus on the linear regression model, but these ideas can extend to other models, but for simplicity, I'll focus on linear regression. And then what I'll talk a little bit about is Bayesian variable selection, and then we'll talk about the approach that we're going to use here, which is going to be selection via the credible sets. We're going to talk the difference between joint and marginal credible sets. I'll give a little bit about the asymptotic properties and some examples. Okay, so here's the main setup. So we've got the standard linear regression model. The response is a linear relation. There's a linear relationship plus error. Just to fix notation, we've got n observations, p predictors. And so we've got x is p dimensional, and so is beta. We're going to assume that the errors are IID. You can, for the asymptotics, you can play around with that a little bit, but for now we'll assume IID. And they have mean zero and constant variance. We're mainly going to be interested in the ultra-high dimensional data where p is much bigger than n. Okay? And the basic idea is we're going to assume some sparsity, so only a subset of the predictors are relevant. And we can identify those by saying beta j equals 0 means it's an irrelevant predictor. Okay, so what do you do? Well, variable selection methods. Well, you can look at all subsets. So 2 to the p is a really large number, so I'm not going to be able to do that. You could do some things like forward selection, backward elimination, stepwise methods. More commonly nowadays with high-dimensional data, people are doing the penalization methods, right, regularization. Or we're going to talk about Bayesian methods, and we're going to actually see the connection between a Bayesian method and a penalization method in this talk. Although there's lots of connections already made, there's going to be a different connection made here. So penalization methods, well, most of you have probably seen this. We're going to minimize squared error, right, the squared norm, plus a tuning parameter times some penalty or regularization on beta. Common ones are lasso, right? The penalty is the L1. Elastic net is another one where it's a convex combination of L1 and L2, right? And that tends to deal with correlation a little bit better than just L1. And there's lots of others. Think of your favorite acronym, and it's probably a penalized regression method. So adaptive lasso, SCAD, MCP, you can go on and on with the list, and there's different purposes of each of them, and so on. So you usually have, so in this case, you've got a tuning parameter lambda. You might have a second tuning parameter or a third if you wanted to, but in this case, you can have 2, and you choose them by AIC, BIC, cross-validation, whatever your favorite tuning method is. And the basic idea is we all know that the shrinkage creates a bias, but it reduces the variance, and it also achieves selection by setting exact zeros. Right? Okay, so what do you do in the ultra-high dimensional data? Most of the time, you're not just going to throw a penalized regression at a huge dimensional problem. Oftentimes, you'll screen down first. Right? So if p is much bigger than n, common nowadays is to do screening first. Sure independent screening is kind of the most popular method. You just do these marginal regressions, and you rank them by the marginal correlation, and you screen down to a manageable number, and then you do a penalized regression. You could instead do a forward selection sequence, and instead of doing marginal things, you could just do the adding one at a time until you get up to a manageable number, and then go ahead and do that. All right, well, we're not going to necessarily do those screening approaches. But what we want to talk about is the idea of what would a Bayesian do in terms of variable selection, whether it be high dimensional or low dimensional. And so what we're going to do is we're going to say, the first thing we have to do is each candidate model, let me just double check the time here. There we go. Just keep an eye on the time for myself. So what we're going to do is each candidate model is going to be indexed by a binary vector, right? So delta, which is 0 or 1, and it's just going to indicate whether that variable is in the model or not. And the next thing we need to do is we need to think about a prior over model space, right? So P of delta, some probability distribution over these binary vectors over model space. The most common is to just say it's kind of a Bernoulli trial type approach. Each one has a marginal inclusion probability, and so the prior over model space is this binomial type thing, just depends on the number of predictors in the model. So you have to pick that prior inclusion probability. Well, probably one of the most common things is to say I'm going to do a uniform prior over model space. And that's the same as saying pi is a half, which sounds reasonable, right? All models are equally likely, no prior information in there, except there's actually a lot of prior information in there. If you say all models are equally likely and p is really large, you're pretty much putting all your mass on models of size p over 2. So on the model size, you're actually putting a lot of information. So there's problems with that. You can change that around a little bit. One of the other things people do is they say, well, I believe about 10% of the predictors are important, so I'm going to set pi to be 0.1. Okay, so you have some a priori guess. The other approach is to say I'm going to put a prior on that. So I have a hyperprior, and beta is the natural thing to do. Okay. Well, now once you have the prior over model space, given the particular model you're at, you put a prior on beta, right? Typically, you're going to do something like sigma squared, the variance gets a diffuse prior on it, like non-informative. You may put, instead of an inverse gamma, you may put a half Cauchy is another common one that people use. And the most common thing is the conjugate normal prior, right? So given a model, I'm going to put a conjugate normal prior on the coefficients. And this variance, you could just put it as independence, or the x transpose x inverse, which is what's known as Zellner's prior. That's computationally convenient because it lines up with the least squares covariance. All right, problem is when p is large, well, that's not invertible, so you could start thinking about generalized inverses. So we're going to focus on using the identity here, just standard, normal, 0, and then a diagonal matrix. Okay, this is equivalent to what you're doing, like what's called a spike and slab prior, where beta is a mixture of point mass at 0 and a continuous part. Okay? So what do? Well, you crank out Bayes' rule, you get the posterior probabilities. Well, you really can't do that for every possible model, so you use what's called stochastic search variable selection. So you'd use an MC-MC chain to visit all the models, and you estimate posterior probabilities by how often you visit a model. You could search for the highest posterior model, which is probably not a good thing to do in high dimensions because all models are probably going to have small posteriors, and to try to find the largest of a bunch of small things is not going to be easy. An alternative is you use the marginal posterior. So Jim Berger has a paper on what's called the median probability model, and you just look at the marginal inclusion probabilities and you threshold it at a half, and that has some nice predictive properties under certain conditions. Okay. So what are some drawbacks of this? And this is why we're going to make some changes. Well, the typical approach, first of all, you need proper prior distributions. You can't do stochastic search with improper priors. You need a choice of prior over model space, which, again, I said could be difficult. You need to decide on what's the posterior threshold choice if you're going to do some marginal things. And to estimate these posterior probabilities, you often need really, really long MC-MC runs because you're trying to estimate posterior probabilities of lots and lots of models. You may need some long runs. And the results can be really sensitive to every choice. The other thing is when you use these marginal inclusion probabilities, when you have high correlation, they could be really poor. Because if you have three variables that are highly correlated, one variable 1 is going to show up, the next one, variable 2 is going to show up, the next one, variable 3 is going to show up. Each one of those variables is going to show up, say, a third of the time. None of them are going to look important, but every model should have at least one of them. And your marginal model is not going to include any of them. Okay, well, there's another problem. Some of you may be familiar with the idea of what's called Lindley's paradox, with using posterior probabilities in general. And let's just think of the simplest case we can imagine, the ultra-low dimensional case. So I've got one observation from a normal with known variance, an unknown mean, and I want to decide, is that mean 0 or not 0? That's really the simplest case of variable selection here. And what you want to do is you want to talk about a diffuse prior. You want to say your prior has no information, so you let the standard deviation get large. Well, if you do that, on the left there, I have a plot. So I have three different y's that I observe. Y equals 0 is the black line. Y equals 2 is the red line. Y equals 3 is the green line. Now, if I observe y equals 3, I should really say that mu is not 0, right? But what happens is as you change the prior standard deviation, making it more diffuse, your posterior probability on mu being 0 will go to 1, no matter what y you observe. That's a problem, okay? Because you want a diffuse prior, but if you're in the region kind of over here, then you're okay. But if you go further, you're in trouble. On the right, what I'm plotting here, you can see the two green lines are paired up, the two red lines are paired up, and the two black lines are paired up. What those are the posterior credible intervals for the same data. Notice how they stabilize, okay? And what they stabilize to is basically the least squares confidence intervals. The observation plus or minus 1.96 times standard error. Well, that kind of hints at, well, maybe we should think about using the credible intervals to do some sort of selection rather than posterior probabilities. And that's what we're going to do. So we're going to say is, I'm going to forget about these priors over model space. I'm going to ignore the fact that I have to put these point masses everywhere and have to decide where they go. I'm going to just say, let's look at the full model. I don't care how big the model is. I'm going to look at the full model, and I'm going to put a prior just on the full model. And I'm going to use a conjugate prior. Everything's simple, okay? And then what I'm going to say is, let's think about a 1 minus alpha times 100% credible region. So say a 95% credible region, for example. And I'm going to say, let's think about constructing a credible region. And in this conjugate case, these credible regions are elliptical. So they're of the form beta minus posterior mean times inverse posterior covariance less than or equal to C alpha for some C that depends on the alpha that I chose. Okay? Now, if I fix tau, I get closed form for all of that. Okay? Everything's conjugate. I can write it down in closed form analytically. If I put a hyperprior on tau, that's not the case anymore, but all I have to estimate is a mean and pairwise correlations. So I don't need to do long MC-MC runs, and they're quick too, because everything is conditionally conjugate. Now, if I put a prior on tau, the elliptical contours are no longer the highest posterior density because the posterior is not a T distribution any longer. In the case of fixed tau, it's a T distribution, so the posterior contours are elliptical. But in general, I could still make elliptical contours. Even if my posterior is not elliptical, they won't be high density anymore, but they're still valid credible regions. So I could still use them. And asymptotically, posteriors become normal and it becomes more and more valid. So the basic idea is that within that region, all possible points within that region are feasible parameter values, right? So what I'm going to do is I'm going to say, well, let's try to find among the region a sparse solution. And I put sparse in quotes because I have to define what I mean by sparse. So I'm going to kind of think about a combinatoric search in the credible region. And this is an elliptical region that I'm going to try to find. And so what I'm writing down now is it's a L0, okay? I'm not going to use L0, but for now we're going to say minimize the L0 subject to being within the credible region. And the chosen model, which is what we're going to focus on, not the estimates, but the model itself, is going to be the set of indices that are non-zero. Okay, well, first of all, there's a problem with searching for the L0, is you got this high dimensional region, and it's a combinatoric search. So I'm going to replace L0 with a bridge that's been used before. It's a smooth bridge between L0 and L1. It's if you look on the limits, there's this A. You look at the limit as it goes to 0, you get L0. As it goes to 1, you get L1. I could use any function here that has some nice properties. I'm not going to use L1 itself because the theory is not going to go through if I just use L1. I'm not going to get the results, the consistency, if I use L1 here. So I'm going to use actually something that's non-convex, and I'll get the results. And the basic idea is we're interested in A close to 0, close to the L0 penalty. So the first problem is it's non-convex. So what's common nowadays is people do a local linear approximation to the penalty, and it's kind of a one-step local linear approximation. So you do a first-term Taylor expansion and around the posterior mean, and you end up now everything is convex, and you can use the Lagrangian. And if you look at the Lagrangian, it's a quadratic form centered at the posterior mean with posterior covariance, plus a penalty lambda. Remember, the credible region was less than or equal to C. Well, now I'm turning it into the Lagrangian formulation, so that's just a Lagrange multiplier now. There's a one-to-one relationship there. And now if you look at the regularization term or the penalty term, it looks like a weighted L1, right? Or an adaptive lasso form. But remember, we're interested in A being around 0. So in fact, once I get to that point, I could just take the limit, let A go to 0, and you'll see the second equation there is what I end up with. So this is exactly the problem that we're trying to solve, right? So I'm turning it around using the Lagrangian, but now this has a nice simple form that all existing software can solve. This is just a adaptive lasso on pseudo covariates, right? I set my x equal to sigma to the -1/2 times beta hat. So I get my initial posterior mean, posterior covariance. That's my pseudo x and my pseudo y, and I plug that into a large algorithm or any kind of algorithm that does the solution path, and I get the entire solution path. So computationally, it's actually really easy now because I turned it into a standard approach. So let's think a little bit about what happens in terms of the asymptotic properties. So what we could think about in terms of asymptotics, we have to think about the sequence of credible sets as I change alpha, right? Because what I really need to do is I need to let alpha go to 0, meaning I need my credible set to go to 100% in order to guarantee that I will have selection consistency, right? It's kind of like saying your tuning parameter has to go at a certain rate. So we're going to just focus on this Cn, which is a one-to-one correspondence with alpha. It's the bound, the contour in the ellipse that you're changing. And you think about the sequence of models. And the theorem is basically that under some general conditions for, it doesn't involve some of the restricted eigenvalue conditions or the, lost the term, but the irrepresentability condition. It's not those conditions. It's a little bit more about just sparsity, the dimension really being of order n, the dimension of the space, for estimability purposes. Otherwise, you can't estimate things. And then, so basically, you have to let it go at an appropriate rate, and you get consistent variable selection. Now, this also holds if you let p diverge. So this is the case where p is fixed and is diverging. It's also going to hold for p diverging, but p over n has to go to 0. Well, that's okay, but it's not completely satisfying, because in the high dimensional case, I'm not necessarily thinking that P is going to always be dominated by N. I want to think about P diverging faster than N. The problem is you could actually show that the posterior mean, since it's of this ridge regression form, you could show fairly straightforwardly that it's not mean square consistent, which means that the ellipse is getting too much volume. It's accumulating too much volume. So we're not going to be consistent to do this. But the nice thing is, you can also show is that even though it's not mean square consistent, if you add up all the terms, it's accumulating too much volume, it's sup norm consistent. So each term will go to 0 in the sup norm, okay, the maximum of all the terms, even when P is diverging. Which then says, well, then maybe we should consider, instead of looking at these ellipses, we should maybe do some thresholding, because that's where the sup norm is going to come in. And so instead of thinking about the elliptical credible regions in the high dimensions, we could think about the rectangular credible regions. So just take that posterior mean and ignore the off-diagonal elements, just look at the diagonal. Pretend after the fact things are independent. And in a sense, this is actually what a Bayesian would have done, who knows, back when Thomas Bayes talked about it, right? Get your posterior, look at credible sets one at a time on each parameter, and threshold them at the right place. Well, that works. That actually has consistent variable selection when the dimension is growing basically just sub-exponentially, right? So it's log P can be up to order n to the c for some c smaller than 1, right? Now, in practice, I wouldn't recommend this thresholding approach over the joint approach, because the joint approach actually works well in practice, although in the very high dimension, it doesn't necessarily have that, the consistency property. And so what I'm going to look at now, just briefly, is a little simulation just to give you an idea. And what I'm going to look at is just the P equals 500, 2,000. I've done larger ones too, but I'm not going to show them here to save some time. N equals 60 observations. P is 500 and 2,000. And what I'm going to consider is the ROC curve, the ordering of the predictors. Not thinking about which model it chooses, but looking at the ROC curve, whether it chose the correct variable or not. And the basic idea to look at this picture is I'm comparing the credible set method. This is the joint credible set method, not the marginal, but the joint. The marginal is very similar, versus the stochastic search. And there's two versions of stochastic search. One thing I want to tell you is I'm kind of cheating here a little bit. The stochastic search, you need all these tuning parameters in there. Well, I know the truth, so I'm giving it the truth. I'm telling it the true proportion of important variables and the variance and everything. So I'm giving it its best opportunity to compete here. But you can see the ROC curve, the solid line is well above. So I've got 0.5 correlation autoregressive and 0.9 correlation autoregressive in the two plots, and you can see the improvement. This is for P equal 500. P equals 2,000, I can't do stochastic search. It just takes forever to run for a simulation. I can't do it. Each one takes too long. I mean, it could be my coding, but it takes forever to run. So I'm comparing it to the lasso here, the L1. Again, you can see when 0.5 autocorrelation, a little bit better, but 0.9, we know that the lasso does really poorly under high correlation, so there's a huge difference here. And so I think, so this is when we look at the ultra-high dimensional case, and I'm going to skip the rest, and we'll, I guess, take questions if we have. On the design matrix, In the ultra-high dimensional case, so basically the condition is really an estimability condition. It's in a sense that that beta is approximately in the span of X transpose X asymptotically. So that's what you end up with. It's like an estimability type condition. I'm sorry, the X transpose X for the good variables. That's what has to lie in the span of.